Welcome to Chapter 3 of the Graph Neural Network series. Today we explore message-passing neural networks, or MPNNs, which provide a unified framework for understanding graph neural networks. Rather than viewing GCN as a special case, we'll see how many GNN architectures, including GCN, GraphSage, and GIN, can all be understood through the lens of message passing. This perspective will deepen your understanding and help you design your own architectures. The MPNN framework decomposes graph learning into two phases repeated over T iterations. In the message phase, each node computes messages to send to its neighbors using a message function, M, that depends on both nodes' features and optionally edge features. All incoming messages are then aggregated, typically through summation. In the update phase, each node updates its hidden state using an update function, U, that combines its current state with the aggregated messages. This simple abstraction is surprisingly powerful. By choosing different message and update functions, we recover GCN, GraphSage, and many other architectures. The key insight is that graph learning is fundamentally about nodes exchanging and integrating information. Let's build intuition for why message passing works. Imagine a social network where people only know about their immediate friends. How does information spread? Through conversations, messages passed between connected individuals. Each person aggregates what they hear from friends and updates their own knowledge. After one round, you know what your immediate friends know. After 2 rounds, that information has reached you from friends of friends. In graph terms, after k layers of message passing, each node has information from its k-hop neighborhood. This is the receptive field of the GNN. The message function decides what information to share, the aggregation function decides how to combine multiple messages, and the update function decides how to integrate new information with existing knowledge. GraphSage, which stands for sample and aggregate E, addresses scalability and inductive learning. Instead of using all neighbors, it samples a fixed number at each layer. The original paper uses 25 first-hop and 10 second-hop neighbors. This bounds computation regardless of graph size. More importantly, GraphSage is inductive. It learns aggregation functions rather than embeddings for specific nodes. This means it can generate embeddings for nodes it has never seen during training. The architecture concatenates the node's own features with aggregated neighbor features, then applies a neural network. GraphSage offers multiple aggregator choices. Mean aggregator averages neighbor features, LSTM aggregator processes them as a sequence, and max pooling applies an MLP then takes element-wise maximum. The graph isomorphism network, or GIN, is designed with expressiveness as the primary goal. The key question is, what graphs can a GNN distinguish? GIN proves that with proper design, a GNN can be as powerful as the Weisfeiler-Lehmann graph isomorphism test, a classical algorithm for distinguishing graphs. The GIN formula includes a learnable parameter epsilon that weights the center node differently from neighbors. HV equals MLP of 1 plus epsilon times HV plus sum of neighbor features. Crucially, GIN uses sum aggregation, not mean, because sum preserves multi-set information that mean loses. 2 neighbors with feature 1 sums to 2, while their mean is still 1. This distinction matters for capturing graph structure. The Weisfeiler-Lehmann test is a classical algorithm for checking if 2 graphs might be isomorphic. It works through iterative color refinement. Start by giving all nodes the same color. In each iteration, update each node's color based on its current color and the multiset of its neighbors' colors. Hash this combined information to get a new color. Repeat until the coloring stabilizes. If the final color histograms differ, the graphs are definitely not isomorphic. If they're the same, the graphs might be isomorphic, the test is one-sided. It famously fails on regular graphs, where every node has the same degree and the colors never separate. GIN's message passing exactly mimics this process, making it provably as powerful as 1WL. There exist higher-order WL tests that are more powerful, but also more computationally expensive. So far, we've focused on node-level tasks, But what about classifying entire graphs? This requires graph pooling to convert node embeddings into a single graph-level representation. The simplest approaches are global pooling. Global mean averages all node embeddings. Global max takes the maximum value per dimension across all nodes, and global sum adds all embeddings together. Sum pooling is often preferred because it preserves information about graph size. A molecule with 10 atoms summing to vector x is different from one with 100 atoms summing to the same x after pooling. We apply an MLP classifier for the final prediction. This pipeline enables applications like molecular property prediction, where we classify molecules as toxic or non-toxic, active or inactive for a drug target. Let's compare the architectures we've learned. GCN uses normalized sum aggregation with a spectral foundation, best for node classification when the full graph is available. GraphSage samples neighbors and supports various aggregators, enabling inductive learning on large graphs where we can't fit everything in memory. GIN uses sum aggregation with a learnable epsilon, achieving maximum expressiveness for graph classification tasks. Coming up, GAT uses attention weights to learn which neighbors matter most, helpful when connections have varying importance. The choice depends on your task: node versus graph classification, transductive versus inductive setting, and whether neighbor importance varies. Often, trying multiple architectures and comparing is the best approach. Let's see message passing in action on MUTAG, a benchmark molecular dataset. MUTAG contains 188 chemical compounds represented as graphs where atoms are nodes with 7-dimensional features encoding element type, and bonds are edges. The task is binary classification. Predict whether a compound is mutagenic. We build a GIN model with 3 layers, each followed by batch normalization and Ray-LU. After the final layer, global sum pooling creates a graph embedding, which feeds into a 2-layer MLP classifier. Training with cross-entropy loss, and the atom optimizer reaches roughly 89% accuracy under 10-fold cross-validation, though with only 188 graphs, the spread across folds is several percentage points. GIN usually edges out GCN here, though on a dataset this small the gap sits inside the fold-to-fold spread. The theoretical reason to expect an advantage is that sum aggregation preserves the multiset of neighboring atoms, which is what distinguishes the substructures relevant to mutagenicity. Let's recap the key ideas. The MPNN framework unifies graph neural networks into message and update phases. GraphSage enables scalable inductive learning through neighbor sampling. GIN achieves maximum expressiveness equivalent to the Weisfeiler-Lehmann test. Graph pooling methods like global sum convert node embeddings to graph-level representations. And different architectures suit different tasks. There's no universal best choice. In Chapter 4, we'll explore graph attention networks, which learn to weight neighbor contributions differently through attention mechanisms. This allows the model to focus on the most relevant neighbors rather than treating all equally. See you there.